Welcome to Who Next. Today we'll be doing CAP 2002 Part B's question 3. So this is the problem. On one fine afternoon, as his family watches from the distance, a man walking barefoot on moist ground near a tower supporting electric transmission lines suddenly stops. So he dies from the shock. Yeah, no big deal. So for about 1 second, electric current of 100 amperes leaking to the ground from a vertical conducting rod whose rounded tip was just below the ground, located 10 meters away from where the man was standing. The resistivity of the moist ground is about 100 ohms meters. So assuming the current spread uniformly into the ground from the rounded tip, find the magnitude of the current density, J, and the electric field, E, as a function of distance, R, from the tip of the rod. So it says we can derive, right, from Ohm's law and bit of dimensional analysis, relation between J and E. So first we know J is charge density, right? So J is just going to be equal to I over your surface. In this case, the surface is going to be a hemisphere. So the surface area of a hemisphere is just going to be 2 pi r squared. Right? So your J is just going to be the current over 2 pi r squared. Right? So you know E is equal to the resistivity times J. So we want to derive this formula in case you don't know that. So we know Ohm's law, right? Everyone knows Ohm's law. V voltage equal to current times resistance. So voltage, right, it can be written as E times L, electric field times length, right? And I can be written as I. Resistivity, you know the formula, R is equal to rho L over A, right? So you can write this as rho L over A, right? So you know I can also be written as this thing. So this is what? J is equal to I over area. So I can be written as J times A. So this can be written as E times L equals to JA rho L over area. So area and area cancels out, L cancels out. You get left with the electric field is equal to current density times resistivity. Right? And this is not this R, right? This is resistivity, like the constant for each material. So we got the relationship, right? J, we got it. It's J is equal to current over 2 pi r squared. Right now I want to find E. E is just this thing times rho. So E is just going to be current 2 pi r squared times rho. Right? So now we got A. I want to find E and J at the victim's locations. So we know this one and we know this one. We know all the variables here. We know current pi, we know rho. We just need R, right? R here. So we're given that the victim was, let's see, 10 meters away. So we can just plug in J 10, plug everything in. We get J is about 0.16 amperes per meter squared. Similarly, with electric field, we can plug in E 10 is around 16 newtons per coulomb. Right? So that's part B. Under any suitable approximation, obtain a reasonable estimate of the potential difference between a man's feet. So let's say we have an average human here. The distance between their legs, well, let's just say 0.5 meters, because why not? That seems like a fair approximation, right? So the extra potential, V, just equal to electric field times distance. This is equal to probably 8 volts. 16 times 0.5, 8 volts, checks out. So it's a pretty good approximation. Is it reasonable to assume that the current went up one leg of the man, across the torso and the heart, and down the other leg? So we know the resistance of the leg is 300 ohms, torso is 1000 ohms, right? So let's say the current goes like up here, and down here again. So we can draw the man's body in the form of a circuit. So you see resistance, right? One resistor here, one resistor here, and it's connected by another resistor. And you have a battery here. So they're connecting in series, right? So your V effective, resistance are effective. Just all three add together. So it's 160 ohms. 1600 ohms, my bad. So we can use Ohm's law, V equals to IR, right? So we get I is equal to the voltage over resistance. We know R effective is this one, and volt we calculated earlier is this one. So we plug this in, we get around 5 times 10 to negative 3 amperes. Right? So now for E. Using your expression for ER, so here, obtain the potential difference delta V between the tip of the rod and the point situated at distance R. Take the tip of the rod to have radius A. So, you know the change, right? Change in voltage, potential difference is just V R at R minus V at A. So we can just do this by taking the integral of the field, right? So R to A of ER dr. Right, we know this is just negative RA. Plug in this thing. It's rho current over 2 pi R squared dr. Right, these are all constants, so we take it out. We get negative rho I 2 pi. All we have is R to negative 2, right? So integrate it, and we just get negative R to negative 1. Evaluate it at R and A. Now we just get cancel out negative signs. So rho I 2 pi and 1 over R minus 1 over A. And this is your expression for the potential difference across delta V, delta voltage. So current ranging from 0.10 amperes to 1 ampere across the torso can trigger defibrillation in the heart. So could this accident have been caused by current that leaked from the rod? Well, actually no, because we know based on our assumptions, the current going through his torso at that point is just going to be 5 times 10 to negative 3 amperes, which is much smaller than 0.1 amperes by like factor of 100 or something. So we know this not happening because he got electrocuted. He just died, lol. So yeah, that's the end.